recollect that what we did last, we stopped in our last lecture on Vorticity vector transport equation. Vorticity transport equation, that is what we did last. And the equation was what? That is the zeta dt is equal to that is equal to zeta dot q plus I think that was what we did last. So in which case q stands for the velocity, zeta stands for the velocity vector. That is the vorticity vector transport equation. So the first term of this equation, this first term, as we said, is the represent the rate at which that is varies, the rate at which body vector varies for a given, fluid particle. For a given fluid particle, when the vortex line lines move, when the set move with moves with the fluid. Okay. Which of course is the strength. The strength of vortex line instead of vorticities remain constant. Diffusivity part of the equation. So this term, this is the term that involves velocity. So this term involves velocity, that is may be looked upon as a velocity transport with regards to the influence of vorticity. So what happens now? If we neglect this part, this is the first part, second, and the third. So if we neglect the second part, neglecting 2, okay, that is the case for which Q is very small, this for slowly moving fluid. For slowly moving fluid, you can neglect that. And this is not large, so that zeta dot q is 0. Is equal to 0 approximately. In that wise, our equation here will change to what? This equation becomes what? The diffusivity equation then reduces to what? Reduces to, see, this part is 0. We now obtain what? That is the z, the t is equal to what? Is equal to del square of this. That's what we get. Okay? So that is what we get. So this is also another form of diffusion equation. This is also another form. This is another form. It's another form of diffusivity equation or positive transport equation. Transport equation. This is another form. In which case, this is assumed to be almost 0. Okay? Now, in particular, it can be shown for two-dimensional flow. In 2D flow, for two-dimensional flow, in fact, it can be shown to be approximately 0 for two-dimensional flow. So let us show that. For 2D flow, this is indeed 0 to be shown. So for two-dimensional flow, it can be shown. For two-dimensional flow, it can be shown that is equal to 0. But let us prove this. Now for 2D flow, as you know, the velocity q is going to be a function of what? It's a function of x, y. Or let me put it this way, is a function in terms of x and y. Say, that is, it does not depend on z. Let velocity q exist for what? For 2D flow. For 2D flow. That is the case that the velocity depends on x and y. Okay? In that wise, what happens? So, what is? That means that I want to, if the velocity in 2D depends on x and y, say, Then velocity Q has three components, which is U. U also depends on X and Y. V also depends on X and Y. V also depends on X and Y. And W. W also depends on X and Y. But we want to assume that, let us say that W is 0. Let us say that W is 0 for 2D flow. Then in that wise, how do we now get our result? Because it's for 2D, W is 0, because in 2D flow, for two-dimensional flow, say this is X, this is Y, so this is Y. So the velocity components along X axis is what? Is U. And the velocity components along Y axis is B. So we are considering flow in a plane. Flow in a plane, or flow that depends on two variables X and Y. This is the component velocity along that, the component velocity along that. So let us consider the type of flow. So if we don't have W components, so we consider that two-dimensional flow in a plane. So in that wise, then vorticity vector zeta, don't forget, zeta is called what? Is called Q. Is called Q. So let us put it using the determinant notation form. That means this is I, J, K. So the components of this, don't forget, is di what? Di X. For the nabla operator, di Y, di Z. Okay? Whereas Q has three components. One of them is 0. Along X, along I, it is U. Along J is the, and we are taking the one along this to be what? To be 0. That's why we say that W is 0 for 2D flow. Okay? Now, can we expand that out? Expanding that, you will get what? If that is expanded, then you get the vorticity vector to be what? Vorticity vector under this equation will be what? So that means direct expansion of that. So that means zeta. Zeta is as usual. The components I. So that means you differentiate this. That means you have the components along I. When it is expanded, this I times differentiate that. That means when you differentiate di Y of 0, the answer is what? 0. Minus, when you differentiate V with respect to Z, don't forget that V depends on what? It depends on X and Y. U also depends on X and Y. It does not depend on Z. It doesn't depend on Z. It does not depend on Z. So therefore, if you differentiate 0 with respect to that, that is 0. If you are not subtracting, if you differentiate V with respect to Z, in as much as there is no Z here, that will be what? 0. Okay? Now we are here. For the components of J, I'm not going to put minus here. This is advanced class. For the components of J, you differentiate. It is this you are going to differentiate with respect to Z. That is the first one. If you differentiate U with respect to Z, because there is no Z here, of course it will be 0. Then minus, you are now here. If you differentiate for the component of this, we have differentiated this, then you differentiate this as well. 0. It's also 0. 0 minus 0. Then finally, for the components along K, of course that is the only one that will exist. For the components along K, are you seeing it? For the components along K, we differentiate this with respect of what X is involved here. So that one exists. That means you have di V, di X minus, we differentiate same. Okay, we differentiate same with respect to this. There is X here as well, there is Y here. So that means there exists also di U, di Y. Okay? This is the result. So this simplifies obviously, and don't let me waste time. It's just 0, 0. So it has only the component of this along K. So you can write if this is I is J and this is K. So that means that this is just going to be di V di X minus di U di Y. The component is along what? Along K. So it is along the vertical. So when the motion is this, let me rewrite this so that you understand what I'm saying. That is to say, what we are saying now it is. So if I write this as let's say this is okay x, let's say this is x y or x y z, because this is perpendicular to this, and this is, so this is along the vertical, that is z. So that means the vertical vector has no component along this, so the vertical vector acts along this. So this is where you expect our vertical vector, because it is along this, and the unit vector along this is k. It's along A, along K is along I, there is nothing, along D, there is nothing. So the only component along this, if I like, I can just write it as di V di X minus di U di Y without putting the vector somewhere. Or if I want to put vector there, I just multiply it by that component. So that is it. So from there, we have seen that vorticity vector acts along that in the case of two-dimensional flow. And of course, it's very easy since you differentiate. What is now this now? Then we need, now that this has been obtained, don't forget, I told you I want to show that this is 0. We have gotten this, but we know our Q. Our Q is what? Our Q is this. This is our Q. Recall that your Q is what? Where Q, velocity, has only two components, which is U involving X and Y, V also involving X and Y. There is no components along W, 0. So that is the velocity. Now, I want to find what is this, the dot product of vorticity vector and nabla. Then what is this? Let's do the arithmetic. Dot this. Okay? What is that going to give you? So if you expand, don't forget, if you had expanded this, it has only two components. Oh, only one component. This is going to be, this one is 0. It has no components along I. It has no component along this. The only component it has along this is this. So if I like, I can represent this by small zeta. I can represent it by small zeta. So that is 0, 0 what? This lowercase. Lowercase zeta. Lowercase zeta. That lowercase zeta represents this. That is what I have here. Represent lowercase zeta. This one is uppercase. It's bigger than this fraction. You can see it. Now, if we were to expand this, so I'm going to dot it with what? I'm going to dot it with what? Then this one is what? It has three components. That is di X, di Y, and di what? Di Z. Di Z. That's it. So, if you take the dot product of this, what do you obtain? Don't forget, from what we have here now, if you expand out, that means I want to, if we expand this is the only component that is left. If we expand it, this is 0 times this. Yes. That means 0 times di X. You are taking dot product. Then you use this to multiply this plus 0 times die y. Finally, you use this zeta, which is just this. That is the only one that will exist. Zeta times what? Die z. Okay? Zeta times die z. Now, I want to operate this on it. So, therefore, so that from this, it follows therefore that zeta dot q is simply what? This is 0, 0. It has only one left. That is zeta. Zeta times die z of what? Of q. But q depends on what? On x and y. It does not depend on z. Yes. You can see q is not depending on what? It's not depending on z, because z is absent here for our 2D flow. It does not depend on z. This is indeed a function of what? X and y. So the result is, this one is just this is die v. You don't need to waste time on that. So when you differentiate a function that is a function of x and y relative to z, the answer is definitely what? 0. So if you use 0 to multiply this, the result is 1. So just as we said before, you know, we assumed it to be 0 when we started with. But in general, we can say categorically, for 2-dimensional flow, this first aspect is generally 0. For 2-dimensional flow, it is generally 0. So that is what we have proved. But, well, it can be proved as well for 3-dimensional, but because most simpler problems in print is 2-dimensional, so just let's take it like that. But we have shown that with confidence that for 2D flow, this part will go, so that we can now write without any fear. I want to rewrite our equation. So in that wise, obviously, so without fear, therefore, we write the vorticity transport equation in 2-dimensional flow as what? In 2-dimensional flow, we start again. We said d with t is equal to what? Remember, we said we have already gotten this one plus what? But this one is what? Is generally what? 0. Is 0. Is 0. That is what we just proved here. That if the flow is 2-dimensional, this eventually is going to be 0. Whatever that this is, because the fact that this one is 0, because this is 0, because this is 0, it will destroy this, so the whole thing is 0. So this aspect is 0. I didn't want to take it for granted. So without law, you can quote without any fear that if the flow is 2-dimensional, then the rate of transport of vorticity, as you can see here, is what? So is equal to what? Of course, this indeed shows the diffusivity of the Vorticity vector. Diffusivity, that is the diffusion, the way. Diffusivity is diffusing through the fluid. The way it is diffusing through the fluid is established by this for 2D flow. This is generally true for 2-dimensional flow. Okay? That reminds me, there's a question I want to ask. You may be asked to prove this at any time, but it's better you go through this. It's very easy. That you should show that starting from this result, starting from this, Then prove that this is 0 for 2D flow. So it's very easy. Just state what you have stated there and then get result. Very elementary. Okay. So this, of course, is a good approximation, what we said before. But could you still remember what is a streamline? How is it related? Question 1. What is question 2? What is a streamline? How is it related to a stream function? Don't forget, a stream function, you did it. Professor Mrs. Akupelu taught you, and I also taught you a stream function. What is a streamline? I'm not going to answer this. What is a streamline? We call a streamline. A streamline is a line. Some people used to call it an imaginary line. It's a line drawn in a free flow such that every tangent to it is along the velocity of the flow. Of course, then how is it related to a stream function? A stream function is such a function related to a streamline. It's such a function related to a streamline, and it is represented by, of course, in most cases, it still refers to this 2D flow. In 2D flow, a stream one, I've answered that the streamline as imaginary line. Imaginary line or curve. Imaginary line or curve drawn in a fluid. Drawn in a fluid such that every tangent to it, I mean to the curve, every tangent to it is parallel to the fluid velocity. Parallel to the fluid velocity. Of course, you know that. You've done it in the class. Just a quick revision of that anyway. So in which case, what are we saying? Is that if, for example, fluid is flowing in this direction, so that's the direction of the fluid flow. That is going to be, there are several, I don't pick particular one. There are maybe a particular case. In which case, if at this place a tangent to it must indicate velocity direction, a tangent to it here must indicate velocity direction, and so on. Here, say that's also a tangent to it. At this place is also velocity, so it varies along. But this line itself is called a streamline, and a streamline is denoted by what? Is as a function is this. Since it is a function of x, y, and it must be equated to what? It's equated to a constant. That's a streamline. There are several streamlines. There are several streamlines, like streamlines along the wing of an aeroplane, the aerofoil, and many others. Now, a stream function, of course, I've shown it here. So this one is streamline. Streamline is a curve. But if now the function itself, we're able to plot the function itself, that is the stream function. And but how is it related to velocity? Relationship with velocity. The velocity as component what? Q. It has to component U, V, because we are working on 2D flow, so we don't need W is 0. So in that wise, therefore, and the relationship is simple. You have done it. You said that U is in terms of what? Yeah, if you differentiate this with respect to Y partially, that is the component of velocity, and V is differentiated partially with respect to what? Respect to X. Of course, the reason why we pick this is that equation of continuity, mass transport, is identically satisfied. Please, if you check quickly, you see that if you take it like this, of course, we cannot change it. This we enable so that by solving, so that continuity equation in what? In 2D is identical. Satisfied. So you can compare it with Kochirima equation under the complex analysis. So what we are saying is you can check if you differentiate U with respect to X, V with respect to Y, of course it will not be 0. Don't just okay, if you differentiate this, that means we are having what? Di X of di psi di Y, which now represents our U, then plus di Y of minus di psi di X. Let us simplify this. Don't jump into conclusion that is 0. So clearly, this is going to be what? Because of this minus what? Di 2. You can write it as di Y di X. But because a string function is a uniform function and it is uniformly continuous, so the order of differentiation is irrelevant, because this function itself, psi, is a uniform function, uniformly differential function or functional. So therefore, the order of differentiation, don't forget analysis, is irrelevant. That means this is still the same thing as what? Di X di Y, and the answer is what? So obviously, this our statement is justified, that in the case of string function, the equation of continuity is satisfied and it is a well-chosen function. It's well-chosen, although it varies with regards to the same line. It's very with regard to several constants, because that constant we put, two streamlines can never cross. So in that wise, that means from here, it follows therefore that our zeta, it has only one component, and the only component is along what? So this is di what? Our zeta, which is di U di Y, we just drawn it, minus what? I just develop it now. Okay.
Di V di Y minus di U di X.
Di V di Y, di V di Y minus di
U
di X. That is it. And if that is the case, if you substitute, what is your V? Something for your V. You can write it in terms of string function. In terms of string function, therefore,
is di V di X.
Di V di X.
Yes. Di U di Y.
Di V di X, di U di Y. Is that?
Yes, it's correct.
So it's correct. So from this you can see if you substitute for your v, what is v, what is u? Our v is what? So our v is, that is dx, or v is minus di psi dx, okay, minus u is what? U is di psi di y, okay. Of course this can be interpreted as what? As minus of what? Minus of x squared plus what? Di y squared. Okay? So, and clearly, you know, we can write this as minus, well, di x squared plus di y squared of psi. And you can use the Nabla notation. It is the same thing as what? Okay, so without loss of generality, we can just use that to represent that. Okay? So, so in that wise, therefore, we can now write our result as what? Zeta. What is going to be zeta? Zeta squared will now be what? Okay, so if that is the case, what is the, our equation now is what? 2D flow. What is transport equation? So, which is what? That is d what? T is equal to is it? That's what we got. That is generally valid. It is generally valid. Then what happens if we expanded this? It can be expanded. This expands as used as total derivative plus you still remember that this, of course, stands for total derivative. So we are now equating this to what? We are now equating it to this. Okay? So, if you now substitute for this, what would this give you? This is now going to be substitute. This one is what? We substitute. If you substitute for this, minus so this is scalar, scalar. This one is scalar. This is also scalar. So the answer is what? Okay, so from here, if the flow is steady, or we can write it as T plus Q dot del is equal to this. What happens if the flow is steady? If the flow is steady, you know, steady means anything that goes with time must be what? Must be zero. If the flow is steady. Therefore, you cancel this. For steady flow, what will you be? For steady flow, therefore, we can write it as what? That means we now have Q dot theta is equal to what? Is equal to minus. Okay, this is also another form of vorticity transport equation in terms of the stream function, and in particular if again if this one is approximately zero, if the right hand side is approximately zero, if Q is zero approximately, then we obtain what? We obtain biharmonic equation, which is what? Because this one is zero, that means the biharmonic equation is what? 4 psi is equal to 0 for the string function. So, I think with this, I'm okay for what we have done so far. The only thing that we should be expecting some exercises on this type of problem, which of course I will give you later. Well,